Hello everybody, in this video we're going to discuss the Riesz representation theorem. In order to discuss that, there are a few ideas that I want to bring across first, and the first idea that I would like to discuss is that of a kernel of an operator. So by kernel of an operator I mean the set of vectors in the domain of the mapping which are mapped to zero vector, which means if I have an operator and it goes from my space X to Y, then all those elements in my space, so suppose Y is a subset of X. Now all those elements, so T of Y equals to 0 for every Y belonging to capital Y. All those vectors which are mapped to the zero vector, they constitute the kernel of an operator. So that's the first thing that I would like to talk about. The next thing is the projection theorem. So let Y be any closed subspace of a Hilbert space H. Then I can write my Hilbert space H as Y direct sum C, where C is the space which is perpendicular to my space Y. What do I mean by this notation? So it means, so suppose C is an element of Z which is equals to Y perp, and phi be an element to capital Y. So the inner product of C and Y is equals to 0. That's what I mean that if an element belong to, so if I have Y belonging to capital Y and Z belonging to Y perp, then the inner product of elements from these two spaces would be equal to 0. If I take any, so let me write it like that. So let me write it like this. For any Z belonging to these and Y belonging to this, the inner product is equals to 0. So that's my direct sum. And the next thing that I want to talk about is that the kernel of an operator is a closed subspace. So if I have a continuous operator T operator, if I have a continuous operator T, then the null space of my operator is closed. This is also one of the theorems that we did in analysis 1. It's a pretty basic proof. You'll find it in any of the books, so I would rather not go into that. So now that we have all the machinery in place, I can finally start with my Riesz representation theorem. So let H be in Hilbert space, and now for each T belonging to H star, which is the space of all linear functionals on H, there exists a unique element xt belonging to my original Hilbert space H, such that T of X is nothing but the inner product of X with xt. So let me break it down. The idea that I want to put across in this theorem is that we are in love with Hilbert space Y because it gives us a very beautiful structure to work with. I do not have this condition in Banach spaces or norm spaces, and I would use this very condition to prove one of the biggest proofs in function analysis, the Hahn-Banach theorem for Hilbert spaces. So with Riesz representation theorem, I have an additional structure to work for my Hilbert spaces, and that's why it's of importance to us. So now let us look at the proof of it. So the result is trivial if T equals to 0, because if T is 0, then 0x. So the result is trivial if T equals to 0, which makes sense. If T is 0, then everything is 0. Case finished. Now otherwise, kernel T is a closed subspace of H, as we discussed before in one of the proofs. And the projection theorem asserts that every Hilbert space H can be written as kernel T direct sum perp kernel T. So this small sign, I can say that if this is Y, I call it Y perp, and I would call it perp of kernel T or kernel T perp. And the kernel T perp is not equal to 0. So now I choose any element belonging to the space perpendicular to my kernel of my T, which means if I have X belonging to kernel T, and if I have C belonging to kernel T perp, then the inner product of X and Z would be equal to 0, because that's the property. And now I said that xt is equals to this quantity. Now note that this thing belongs to kernel T. Why does it belongs to kernel T? Very simple. So what you can do if you want to check that if anything belongs to kernel T, what do? I just put a T around of this. T of all these things, which would be equal to, I'm so sorry for writing in a compact way, but I think the main idea is across. Or rather, let me write it in a nice way. So T of Tz x minus Tx z is equals to Tz Tx minus Tx Tz, which is of course 0, which implies that this is an element of kernel of T for every value of x belonging to my space H. Now if this thing belongs to the kernel of T, then if I take the inner product of this quantity with my z, that should also become 0. If I multiply z inside, what I eventually get is this quantity. See, I solve this and this is what I get. And now if this thing is equals to 0, I take T of x on the other side, and this is the formula that I get for T of x, because that is how I defined xt. So I can say that if I multiply this inside, then I can write it as x comma xt. This is what I originally wanted. Now another thing I want to show is that there is a unique element xt. There's not just any element. I need to prove the uniqueness of my xt. How would I prove that uniqueness? I would take any two xt's. And now in order to prove uniqueness, so suppose I have two xt's, so I call it xt1 and xt2, such that T of x is equals to xt1 is equals to this. Now if I have two xt's satisfying this condition, then I take it to the other side. So let me take it to the other side. Minus this thing is equals to 0. Okay, so now I have this equation, and once I have this equation, then I can prove the uniqueness. So hence proved.